Okay, so I did do screencast 7 and 8, and I did send them to you a while ago, but I was looking at my grades today finally, and I noticed that I was missing a few labs, which I knew I did today, and I just figured to read over the screening reviews and see if I missed something, or I never got feedback on either one of them. Just so that you know, I did send them. They were right there, Morrison. I did send screencast 7 and screencast 8. Um, Although I never got feedback on it, there were YouTube videos as the usual ones I do, so I just decided to redo them, whatever I thought I did wrong in the previous ones, to see if you were okay to do that. So I know I sent the other ones, but I just kind of am going to redo them because I think I might have done them wrong. Anyway, so the question for screencast 7 was two people push in opposite direction on a crate standing on a frictionless surface. The crate is initially at rest at point A, then moves to the left without rotating, then ends up at rest at point B. Then how much work is done by each person? So it's pretty simple. I think I did it wrong before, so I redid it again. I drew the free body diagram. At point A, person 1 is pushing this way, person 2 is pushing this way. Now I moved to the left direction, which indicates the person 2 is probably going to have a greater force pushing that way in order to get it to move. It needs to have a greater force. So we could count the negative force this way. I didn't actually plug that in. I just plugged positive forces. But if we're to do that, count this a positive direction. So the work done by person 1 would be negative. I just didn't put it in. So it'd be here. It would be negative force. But either way, I didn't plug this in, but either way, even without the negative sign, force equals, so a work done by person 1 is force times distance. Force is the mass times acceleration. So in order for us to get it to move, this force needs to be greater than that force. I already know that. So the force on person 2, I figured that the work done by person 2 needs to be double the force, and distance is going to be the same. So F would equal 2ma. The force would equal 2ma. The way I did that is, so I figured that the force done by person 2 will be greater than person 1. Now, I know that the distance from A to B will be the same for both people that the box moves. In their acceleration, if the people are pushing with the same exact force that they started with, the acceleration of the box will be the same, will be constant from point A to point B. So work done at point A to point B, work done from point A to point B, P2 or person 2 right here is going to be greater. The work done is going to be greater by person 2. Although, if you go down, at point B, in order to get it to stop, person B needs to create a bigger force on to the box than person 2. So person 1 needs to create a bigger force than person 2. So in this case, work of person 1 is going to equal 2FD, and then work of person 2 is going to equal FD. The reason of that, so the total work done by each person, if we don't even count the negative and positive signs, I kind of didn't do that, because even if I did, this would be negative F 2FD, and that would be negative, and negative plus negative is still negative. Well, the total work done without counting the negative signs is the way I did it. So the work initial done, this is by person 1. So person 1 was to the left. So in the beginning, person 1 just did FD, and at the end it did 2FD. I kind of used common sense for this, like what would happen if me and my sister were to push a box from this point to that point. And then that would equal, I just kind of did like math arrows in order to figure this out. 3 of D2, D2. And then the work done by P2 would be this person. So they exerted a bigger force into the beginning to get the box moving. And then at the end, they slowed down the work. So it's going to be 3 of D2. So they're actually going to equal. They are going to equal. So from the start to the negative, so if we add up the work, these two works, and then these two works, they should equal each other. So if we equal work initial of person 1 and then work initial of person 2, it should equal the work final of person 1 to the work final of person 2. So the work done from point A to point B should be the exact same, and then the which means also that the work done by person 1 and person 2 is going to be the exact same. So that's to question 1. To question 2, I'll go a little faster. It said, suppose you're climbing a rope that is hanging freely from this gym ceiling. What is the of an age height? So we have the height, and then what is the work done on the person by gravity? Well, gravity going down is 9.81, but it's positive. If you're going against gravity, it's going to be negative. So work done by gravity on a person is going to be FD, which FD in this case is going to be equal negative mgh. So the work acting, gravity acting against person, okay? So that's going to equal, so which means the work is negative. So work is going to equal less than 0. Work done by gravity is going to equal less than 0. And that's a free body diagram because person's going up against gravity and gravity is going down. Now in 2, work on you by the rope. At first I thought it was 0 because the rope is not moving. Then when I thought about it with a hint, determine how the hands move on the rope, I figured out that there's friction. And then I had to figure out if there's static friction or if there's kinetic friction. Well, the rope is not moving, the hands are moving. So the force matches the applied force. So the work done on the rope on the person is going to be the static friction, the coefficient of static friction, which is going to equal coefficient mg gravity, and then h, which is the distance, mgh, which is going to be the distance up the rope. So, and it's going to be static friction. So whatever that would be the work done on the rope on the person. Though we need to know the mass, we know gravity, and we need to know the height, and we need to know the coefficient of the hands on the rope, or the rope and the hands. So that's my answer to question 2.